Okay, now let's assume diffusion along the rod. That's what we've done so far. And lateral heat loss or gain through the sides. So, we've got our rod here, and, again, we still have our, maybe a T1 and a T2 here. But now, this is our U of X and T. But now, let's say we uninsulate it, and in this case, we have sort of some ambient temperature out here, U0. And this heat, we aren't sure whether, if it's hotter, the heat will travel in. If it's colder, the heat will travel out, one of those two. Now, what we assume, and this goes back to Newton's laws of cooling and so forth, assume loss is proportional and it's actually a rate of change of loss, I guess, is proportional to the difference of U and U0. So that's Newton's law of cooling. That typically, if you were just looking at a straight time sort of problem, you would have something like U sub T is, some beta. We'll put a minus on this, U minus U0, something like that. So we do the same thing here. We assume that loss is minus beta U minus U0. And notice then, if U is greater than U0, we look back up here at our picture, if the heat, temperature of the rod is greater than the ambient temperature, the rod should lose heat to the environment. And so, then U sub T is more negative. I'm not going to say it's negative because of the diffusion term with the second derivative, but it's more negative. And so our new model this isn't the complete model, this is just the heat loss part. So I'll put off heat loss is U sub T. Now we still have the diffusion part where the heat can move along the rod, but then minus beta times U minus U0. And here we're assuming that beta is greater than 0. Okay, so depending on the relative sizes of alpha squared and beta, we could see that either lateral heat loss or again gain or lateral, let me do it this way, lateral heat transfer dominates the diffusion, or vice versa. Could go either way. Now it's interesting, and this is the great thing about math models and so forth. This model can also be applied. Instead of looking at heat, this could be applied to some chemical reactions. Oops, reactions. You know, where maybe you're making one substance out of another. So where, in this case, the minus beta U minus U0 term reflects the rate of change of reaction involving the two concentrations. So in this case, our U's, instead of being heat, would be chemical concentrations. And, you know, as you build one chemical from another, the difference in their concentrations can definitely affect the speed of the reaction. And so there you go. There's the lateral heat loss model.